Mew, I'll never let go. I'll love you forever. This chapter is a big deal because, in a sense, this entire class is meant to teach you hypothesis tests and confidence intervals. So we've done hypothesis tests. Now we're going to get the other half of what this class is all about. And the rest of the semester we're going to spend doing these two things for different versions. Now, with hypothesis tests, we ask the question, given a parameter, and the parameter we've been chasing is mu, how likely is it to get data like this? So we find the probability of that data, that's called a p-value, and then if the p-value is small, it means your data is really unlikely, and that makes us doubt our mu. Or if the p-value is very big, it means this data is very likely, and so that mu is reasonable. Confidence intervals are doing the same thing from the opposite direction. Given the data, what are the values for the parameter? And again, it's going to be mu we're going to chase, which would be likely. In other words, looking at the data, what's the range of values for which I'm going to say mu is probably in this range? I hope you can see how these two statements are very similar. They're asking the same kind of question. What's likely and what's unlikely? Here, we start with a mu, and then we find a probability for the data. Here, we start with the data, and we're going to end up saying, here's a range of what's likely for mu. Let me show you what I mean with a picture. Here is the distribution of x bar. That means we call this a sampling distribution. And right in the center is this mu. Mu exists just because we don't know what it is, just because we have no idea what the actual value is. It does exist somewhere. Now, we had a little morning session for mu at the beginning of this video because, let's be realistic, we're never going to know exactly what mu is. But we do know x bar. If we know x bar, can we say something about where mu ought to be? Well, let's answer that question backwards first. Based on this mu, where is x bar going to be? Well, x bar is probably going to be close to mu. X bar might be a little bit off from mu. In fact, x bar might be a way off from mu, but it's not going to be clear out here very often. So I'm going to say most likely it's going to land in this range. And I can change what that range is, but most common is to say 95%. In other words, 95% of the time, x bar lands here. So 95% of the time, maybe x bar lands here, or x bar lands here. Sometimes x bar lands out here. Sometimes it lands outside the bounds. How often? Well, there's a 5% chance it lands outside the bounds. We've got a 2.5% chance it could land here, and then we've got a 2.5% chance that it could land over here. But 95% of the time, x bar would be landing here. I realize in real life we only get one x bar. But imagine the idea of a sampling distribution. So I'm going to be the x bars that you can expect to get, hopping around in this range, occasionally in that range. Well, what if I, as x bar, steal these bounds? Okay, there's the bounds that mu was using to say where x bar should be. Now x bar is going to steal them. And what happens as x bar goes around here? This, by the way, has a name. It's called the x bar dance. And if you want to get up right over where you are, your roommates will not think you're crazy. You can do the x bar dance with me. Notice, however, 95% of the time, x bar is in these bounds, and that translates into 95% of the time, mu is also in these bounds. Now, is it possible mu won't be in these bounds? Yes, 5% of the time I can be out here, and then these bounds won't capture mu. But 95% of the time, it will be. In other words, 95% of the time, mu and x bar are going to be this far apart. So let's give that a name. We're going to call it the margin of error. And because we've worked with sampling distributions, we know how to find this margin of error. This margin of error is so many z-scores away from the standard error. Z sigma over square root of n. So if I go mu minus z sigma over square root of n and mu plus z sigma over square root of n, that's the range that should capture x bar. If x bar steals those bounds and x bar goes minus z sigma over square root of n and plus z sigma over square root of n, then mu is expected to be within that range. Let me show you the idea mathematically. Here's the equation that we have for a confidence interval. And we have a mu, and we get a z, so we find probabilities. Now, let's go the other way and say, what would this equal if I solve for mu? And this is a trick you're going to want to learn, because this trick makes it so that the class is twice as easy. You will have half as much to remember. So I'm going to take this to the other side. That leaves me with z sigma over square root of n equals x bar minus mu. Remember, I'm trying to get mu alone, so I'm going to move mu to this side, and I'm going to move all that to the other side, z sigma over square root of n. And now, if my z is both positive and negative, I can write the positive negative there. This is called the equation for a confidence interval. What does it say? Well, there's two equations. You're going to do it twice. One, you're going to do x bar minus z sigma over the square root of n. And the other one, you're going to do x bar plus z sigma over square root of n. Two different answers. What do those two answers give you? Well, from x bar, they're stealing a margin of error on the lower side, and they're stealing a margin of error to go on the upper side, and that's a range around x bar. If x bar is supposed to be that range away from mu, then conversely, mu should be that far away from x bar. So we can use these bounds to say, I think mu is reasonable within this range. Blah, blah, blah. It wasn't that useful. Knowing I'm on camera makes my nose itch.